All right, we'll take a look. So today we'll take a look at I don't know, I guess some more graphic stuff in Python with Matplotlib and also maybe Seaborn. Okay. All right. So anyway, just as always, here. Let me do restart and clear outputs. Okay, so we import NumPy, Pandas, Matplotlib. And then and here I'm just plotting x versus x, x versus x plus 1, and x plus 2, and you can specify colors. And you know, anytime you call a plot, it defaults to creating a line plot. And so so here I'm going to have blue, green, and red. And ta-da, there you go. And then you have other shortcuts for single colors. So blue, green, red, yellow, and black is K. Okay, so this uses kind of your standard, I don't know, RGB and CMYK from like the printing stuff. So those all have single character shortcuts, and then I think last time we also saw the named colors like navy and rose red or whatever it was, misty red, something. Okay. You can also change. There are 4 styles for lines. Okay, and they look like this. You've got dash. You have the solid line, dashed line, dash dot, and the dotted line. Okay, so this is just, these are the 4 styles of lines, and by default, if you don't specify a color, maybe I'll is that by default it's going to use different colors anyway. So anyway, here's the line, the dash, dot dash, and the dotted. Those are your 4 line styles, and that's it for line styles. And with that, you can make a bunch of line plots. Okay, so here you can use the figure argument. Maybe why is my keyboard not working? There we go. Right, and this covers all of the kind of optional arguments you can have for figure. Maybe I'll let me insert that in here. Just write documentation. Okay, so here I can define the size as 4 by 4, so it'll make a square. Then you have to define the figure first, so it knows how to plot it, and then I'm just going to do a XY scattered. So this is just random positions. So this is just uniform random values spread out here. Okay, and that's using PLT scatter. So if you want dots, PLT scatter, otherwise you're going to get a bunch of lines connecting all of these things. Here I'm going to randomly choose values from 0 to 10 and multiply it by 100. Okay, and so I'm going to have sizes from 0, 100 up to 900. Okay, and then I'm going to also choose random values from 0, 5, so 0, 1, 2, 3, or 4, and I'm going to use these to specify colors. Okay, so as far as colors go, I'm going to use, I've got this array, RBGMY, so red, blue, green, magenta, and yellow. And then I can subset the colors using the integers in W. Okay, and so this will correspond every time it sees a 2, it's going to pull out G, it sees 0, and it's going to pull red. Okay, and so I can use these vectors, this color vector with the RGB, Ys, and Ms, and this numeric vector with values from 0 to 900 to kind of create my scatter plot this time. So this time I'm going to make a larger scatter plot, 8 by 8. We're going to plot the same x and y values. And I have s equals to z. S is like the size or the scale. And I'm going to set the scale equal to this vector here. And c will be equal to the color. Okay, so c will be equal to this color vector c. Okay, so I'm mapping the size s to the variable z and color to c. Alpha 0.4 gives it some transparency, so when they overlap you can kind of see the values underneath. If I didn't have the alpha term there, then they would just kind of obstruct each other. But alpha gives it a little bit of transparency there. Okay, so it looks like that. You can change the markers. Okay, you can use any of these values. Points, the default is the circle marker, but you can also say, like, I want stars, I want squares, triangles, and things like that. So you can say the marker here. So if you give it an asterisk, it makes stars, which suddenly seems like very cheerful. But you can also say I want squares or whatever you want, right? And then there's all sorts of stuff. An X and a plus. X markers and plus markers. Okay, but anyway, we'll go back to the stars. It makes me happy. Okay. The only thing about you can't, so like in ggplot, you're able to like map any variable to pretty much any other aesthetic trait. Okay, you can't do that with matplotlib. Okay, you can map colors and scale to you can map a variable to the aesthetic traits color and scale, but not to the marker. If you do want to do something with the marker and indicate different things, that is possible. Okay, so here I'm just pretending that the first I guess the first 10 values, I guess I should have done whatever. The first 10 values are going to be, I'm using size 100, red. We're going to use stars, and we're going to call this group A. The label just serves the purpose of the legend, okay? And then here I'm calling scatter again, this time with different numbers, color blue, and the marker will be the circles, and we're going to call that group B. And then when you call plt.legend, it's going to use the values that you put in label. Okay. If you don't put in a label argument, then it doesn't show up in the legend. Okay. So the label is used for the purpose of making the legend. Okay. If I didn't put in the argument to create a legend, it would just plot it, and this label argument doesn't matter. But throwing in plt.legend automatically creates a legend for you, throws it in the corner, and shows how they are indicated. All right. Okay, so that's you know, kind of, you know, this will probably cover most of your plotting needs. Okay. In Matplotlib, you also have the ability to make subplots. Okay, what a subplot is it takes the entire figure and breaks it down into smaller chunks here. Okay, so what I've done is I've said for the range 1 through 7, or in this case 1, 2, 3, 4, 5, 6, create subplots. Okay, the first two arguments of subplot is how many rows you want and how many columns you want to divide up the entire figure. So I have an entire figure that is arbitrarily, you know, 9 whatever imaginary units wide and 6 units tall, and we say, okay, let's split that up into subplots, where we're going to have 2 rows of subplots and 3 columns of it. Okay, and then the third argument in the subplot is which of the subplots you want to work in, and so 1 is going to be at the top left, and these so subplot uses MATLAB indexing, which starts at 1. Okay, and so here, you know, it just goes 1, 2, 3 across the top, 4, 5, 6 across the bottom. And so anyway, I just made I called PLT text. PLT text just allows you to print some text onto you know, whatever plot it is. You give it the coordinates of the text. In this case, 0.5, 0.5 puts it right in the middle. And then the text that you're going to write is plot with you know, 2, 3, I as the string. Okay, convert 2, 3, and I into a string, and then you can say, you know, center. You know, if you want left, then it will left use that 0.5, 0.5 location as kind of the left starting point. But I think it makes sense to use center here. And so that, you know, if you wanted to, you can also, you know, add text to label the points in some graph or something like that as well. You can use something called grid spec to make complicated grids. I think this is more trouble than it's worth, but it's here. I'll just kind of show you. All right. So grid spec, much like subplot, you give it like how you want to divide up the plot. Okay. And so in this case, we're going to say 2 rows, 3 columns, and then you can specify how much space goes horizontally and vertically. Okay. And then when you call the subplots, grid spec uses 0-based indexing, but grid 0, 0 will draw a subplot in the kind of the top left corner, and then here the subplot 0, 1 colon will create a plot using in the top row. So this will be top row, but columns 1 through 2, right? Because it's because we've specified which the remaining columns here. Does that kind of make sense? What's going on here? When I say grid spec 0, comma 1 colon, I could just as easily write 1 colon 2. Oh, I'm sorry, it's using slicing, so 1 colon 3 here, and it specifies. So it's like the you know, the grids are numbered, and you're saying like which of these spaces you want to use for a plot, if that makes sense. Okay, and then you can and then so for each of these things, for the subplot, you can then plt.scatter, I don't know, let's just do x and okay, and this will show up in this plot here, and then I don't know, you do something like plt hist. So after you call subplot, it tells Python, you know, which group, which thing it's working in. So I can do a histogram of x, and it creates a histogram in that plot and whatnot, right? So and this is, there you go. Okay, so the subplot tells it, you know, which plot to work in, and then what you want to throw in each one. Okay, and this is just one figure. So, you know, we can do plt.figure fig size. I forget. The fig size is equal to I don't know, 10 comma 5. Ta-da. Okay, so that's but yeah, I mean, this is that's if you're trying to get like pretty pictures and stuff, right? I think I would probably, just personally speaking, I would just be lazy and just make one plot and then one plot right after another. But but if you want to format them, you know, you can do it. Okay, this is like a pain in the butt. This was an example that was in the textbook, so I just copied it. Okay, this is like too much trouble for me. But here I did what the textbook did was it did grid spec. Okay, 4x4, a 4x4 grid. Okay, and then it defines. It's using it calls add subplot, which creates these subplots. Okay, and so here we're gonna create kind of a main picture. Okay, which is going to be the result of, you know, our subplot here defined by the grid. Okay, and then y histogram and x histograms, these are all just, we're calling subplots on these things. Okay, you can specify other things like share the x-axis with the main plot and things like that, and that just kind of aligns all of the axes together. And then on the main plot we create a scatter plot using I guess plot, and then the option O will create a scatter plot, and then on the x and the y histogram plots we're creating histograms here, and then we get this thing to show. We have a bivariate normal, and then if you look at each one independently, they're also normal. Although again, this is probably too much work to be worth it. There's things that do it for us automatically. So, all right. The other plots that you'll probably, so line plots and scatter plots are quite common. Histograms you might use. Okay, and then here's just a few options for the histograms. So here, if we just generate data randomly, you can just do plt hist and show the histogram. You can specify the bins, and you can specify the transparency and colors. Okay, and now I have a histogram of the exact same data, but with more bins. There's another histogram called step filled, and that gets rid of the lines between the bars. Okay, it kind of makes a single shape here, and this is, so it's the exact same shape, but I don't know, it represents it this way without the lines in between. Okay, let's turn off alpha. So this is, so that's that. If you want to make a whole bunch of stuff, okay, you can use something called Kwargs keyword arguments. And so, you know, here I created a histogram with the arguments bins is 25, alpha is 5, 0.5, color is steel blue, and edge color is black, and things like that. And I might want to create a series of histograms where we've got where all of them will be the histogram type will be step filled, and we want alpha transparency level to be 0.2, and we'll say we want to plot the density. Density is true, and we're going to use 40 bins. Okay, and so, you know, the traditional method would have been, you know, take these arguments and then just copy and paste them for this histogram, copy and paste them for this histogram, and copy and paste them for this histogram. But then maybe later on you want to change something, and then you got to change the thing in all 3 locations. Well, you can use Kwargs keyword arguments, and I think this was covered in one of your data camp things, right? So you can use Kwargs, and you'll call star star on your dictionary, and then it will basically fill in these extra arguments. So here we're creating 3 x variables, x1, x2, and x3, and they're all normally distributed, but they've got different means and different standard deviations. And then we're going to create overlaying histograms of each of them, and they're all going to use these same arguments here, right? And here's our resulting plot. And then, you know, if I wanted to, I could just change the argument in the Kwargs and the keyword arguments, and then it would modify the results for all of these things, right? So if I got rid of his type step filled, I guess I would have to define edge color first. Okay, so we would get something that looks like that versus and now we have, you know, these shapes here. And you can also, you can use the keyword arguments and then stick in additional things like, is it a histogram? Is it color? I don't know. Let's call this navy, right? And that works also. So you could, you know, override any of these things. Edge color, oh, I think, oh no, I didn't like that. Okay. All right, I guess you can't override it if you got it specified in the things. Okay. All right. Matplotlib also has 2D histograms. All right. And so here you can, I'm using the multivariate normal variable generator, value generator in NumPy. So I got NumPy random according to the multivariate normal. And so they'll be centered with mean 0, 0 and covariance matrix 1, 1, 1, 2. Okay, and we're going to ask for 10,000 values. When you transpose them, you'll get, you know, a vector x and a vector y that you can then capture using tuple unpacking, right? And then you can ask for a 2-dimensional histogram, and that's what it will create here, and it looks like this. Okay, the color bar, if I didn't use that in there, you would just get this. The argument color bar kind of creates I'm sorry, kind of gives you a key to help you understand the numbers that show up in here. Okay. And then if for whatever reason you wanted to make 2D histogram, but with hexagons because they're pretty. You know, you've got that option as well. As always, I'll just kind of point you to the matplotlib documentation, and you can always look at examples, and you're like, oh, how did we do that? You know, you can just kind of take a look, right? And so this, which was probably way too much work, can be done with all that code. So anyway, that's that. Okay, there is a package called Seaborn, and Seaborn does a lot of stuff that I don't know, just makes plots like data exploration, visual data exploration, maybe easier. They're like little shortcuts for pretty graphs. An important thing to note, though, and the general alias that we frequently use is SNS for Seaborn. Okay, I mean you could just call it import Seaborn. And we've already imported matplotlib, numpy, and pandas. Okay. With Seaborn, you are able to fit like linear regression models and stuff, but the point of Seaborn is not this model fitting stuff. So you can fit a trend line, but Seaborn will, like by design, will not tell you the slope and intercept of that trend line. It'll just draw a trend line, okay? But it will not tell you the coefficients and things like that, because they don't want you to use Seaborn as a way for analysis, like doing statistical analysis, mostly just for exploration, okay? And so with Seaborn, you have, instead of histogram, you'll have dist plot, which will create a histogram plus a smoothed out kernel density estimate of the thing, okay? So here, well, okay, let me turn off SNS set, and this will, here I've just generated 100 random normal values, and it does this. We often will just throw SNS set, and this will set aesthetic parameters. These will use the default ones, which look like this, but you can Seaborn set, and I don't know, there's all sorts of styles that that you can use for Seaborn, controlling figure aesthetics and all of this. Okay, so yeah, the Seaborn. So if you don't call SNS set, it uses the matplotlib defaults, and then SNS set will use this. We'll call the Seaborn aesthetic defaults. Okay, uses the Seaborn aesthetic defaults. Okay, which looks like this. So this is kind of the difference between this and this. And okay, so anyway, now that we've done that, so so here you get the histogram plus the kernel density estimate. You can specify options in dist plot. You can turn off the kernel density estimate. You can change the number of bins. You can run rug equals true. A rug plot basically puts little ticks at the location of each value. So with 100 data points, we're going to have 100 little ticks here that kind of shows you where the values are located. And you can see out here I've got one tick, and therefore my bar has a height of 1. And then if we look super closely here, there's 3 little ticks here, and so this bar that corresponds here has a height of 3 and things like that. So the rug plot shows you all of this. And you can set any of these things. So true will we'll throw that in there. False, we'll remove it. By default, rug is not turned on. And then, as always, you can just go to the documentation for distribution plot. Okay, and there's all sorts of things, right? So the histogram, yeah, if you don't even want the histogram, you can turn that off as well. So here I turn histogram false and rug true, and you have this, and you have all of that. So you can the histogram, the KDE, kernel density estimate, rug, all sorts of options here, and these are some of the different things you can make. Okay, and then if you want to mess with parameters for like the kernel density estimate, like the bandwidth, you can directly call Seaborn KDE plot for the kernel density, and you can mess with the bandwidth. Change it from 0.2 to 2, which will make it like super smooth, right? You guys are familiar with KDE, kernel density estimates? Sort of. It's like, here's a histogram and draw a smooth. Like if you had to draw a shape, okay? And that's effectively what it's doing. What it's doing is it's dropping little hills that stack on top of each other at every location, centered at each location of the dots. And then when they stack up, you get this looking shape. Okay. Here we had we created a bivariate plot, and so here I created a data frame with x and y. So I used the multivariate normal random generator in NumPy, and I made a data frame with columns x and y, and then joint plot. So instead of having to go through all of this trouble, I don't know, of specifying grids and whatever, which is a pain, you can just call joint plot on this, and it makes the scatter and the histogram, okay, which is like, oh, that is like way easier, right? And so for visual exploration, stuff like this just makes your job way easier here. Okay, you can change it to here's one of the arguments. Change the kind to KDE instead of the default, and then it creates kind of these contour density estimates and density estimates for the individual variables themselves as well. Okay. These are just, so the joint plot is handy for two-dimensional data. Okay. You can do pairwise plots. Okay. So in R you have the argument pairs, the function pairs, and that creates pairwise plots. And so that's like if you have a bunch of numeric variables. So here we've got dataset iris, and which has 4 columns of numeric variables, and the pair grid plot will plot each one against each other. So you get a scatter plot of one variable against another one. So I've got 4 variables, 4 numeric variables, and so each one you can create scatter plots, and so I can plot the numeric variable sepal length versus petal width, and this is what the plot looks like. And then when it looks at petal width by petal width, it's going to create a histogram of each one. Okay, and then the others, you just get these pairwise plots. I think Seaborn pair plot, and then there's, so this is the default, and you can change change these things. Hue equals species, okay? And so you can map, so within the iris data set, there was, there's another column that corresponds to the species of the variables. And so here I'm gonna just go ahead and call this, copy it. And so if you map one of the columns to a categorical variable, it can color the dots in the scatter plot accordingly. Okay, so this just makes some of this data visualization like way easier. And then you can easily start to identify clusters, right, within the data, which is why the iris data says a favorite for classification algorithms here. Okay, here I've got, there's a data set called tips, and this was looking at like restaurants, and they looked at the total bill of the restaurant and how much the person got, how much the customer tipped. Okay, so so I guess this must have been back in the day when people paid with cash. So this is like they paid $18 total for a $17 bill, and this person paid, I guess, $12 on a $10 bill and things like that. This must have been a while ago, and things like that. So anyway, here's kind of the data that we have, and you know, was it dinner and how many people were in the party. 2 people ate for $17 plus $1 tip. You know, that's, can't do that anymore. This is like 1 burrito at Chipotle now, right? So okay, but anyway, you can create, you know, these different things, such as the strip plot, okay? And this kind of creates it's like a dot plot, but you know, with a little bit of jitter. And so you can kind of see the dots. And here, by default, because I've mapped the categorical variable day to x, day goes on the x-axis, okay? Total bill, which is numeric, shows up this way. And then the data coming from the tips data set. Okay. All right. Why is this? I say jitter. I guess jitter is false. Okay. So jitter equal. I guess the default is jitter false, or is jitter true. So with false, they all get plotted on top of each other. That's no good. Jitter true, which I guess is the default behavior, will spread them out a little bit so you can get a sense of distribution. Okay. Seaborn has all of these names for plots that I've like never really heard of before. Okay. So swarm plots are basically the same thing as these things, but they make them symmetric. Okay. And then here I specify the color to be the same for everybody, but it doesn't have to be, okay? So swarm plot basically takes the same information but makes them a little bit more symmetric, okay? And here I'm going to change the variable sex to the hue or the color of the dot, okay? And then so here we get the same swarm plot here, except it's not colored by the x variable anymore. It's colored by whether the person was male or female. And I don't know if this is helpful or not, but we have that. Okay. here if I map the categorical variable day to hue, it's going to be pretty much exactly the same as this. Oh, I'm sorry. I have x mapped to sex. If I did x is day and the hue is day, then we get the same plot as what we have over here. But in this one, I mapped x to sex and hue to day. And then you get this thing, and you can compare the overall male total bills versus female total bills. There seems to be a slight difference between male total bills and female total bills, but it's hard to tell what the difference is between days because these colors just hurt my eyes, and I can't tell what's going on. Okay, so probably colored by the day, but the colors aren't helping me. Now over here, it does seem like, I don't know, there aren't very many people eating on Fridays, which is surprising, but then I don't know. Okay. All right, you got box plots, which is exactly what you expect. And again, you can I must have duplicated this. Oh, wait. Oh, here, I'm sorry. Y is the day and X is total bill. Okay, and so I just make some horizontal. So those are box plots. And then again, you can color based on hue, all right? And for box plots, then you end up getting these side-by-side box plots colored by the sex, okay? And then you get these things called violin plots, which I've never heard before until Seaborn, and they look like this. And there's a funny XKCD comic on violin plots, and I'll just leave it at that. But anyway, I guess they're kind of like KDE estimates on for each thing. Okay. Okay, and then we're gonna run out of time here. We have something called facet grids, and facet grids are pretty awesome in that what it does is it takes a variable, and it's kind of like applying a group by, and it separates the entire data set based on some kind of categorical variable, and it's going to just plot that subset of data within each, I guess what it calls a facet. Okay, so here I'm going to set up a facet grid, and we're going to set up columns based on the sex. Okay, and then we call the function map, and it's going to run a distribution plot on, which is basically the histogram, okay, on each of the facets that have been created by facet grid, okay, and it's going to create a distribution plot of total bill. And so what this does, so facet grid creates, here, let me just kind of comment this out. Okay, so facet grid creates basically two subplots, but the one on the left will be for one sex, and then the one on the right will be for another sex, okay? And then if you want a plot to show up there, then you call, you map a graphic command, like in this case, distribution plot, and it's going to do distribution plot for total bill on this side, which has been subsetted for males, and this one will be has been subsetted for females over here. Okay. So you can create facet grids based on the column. Here I'm going to create facet grids where the row is based on the day. All right, and if I just do this, it creates 4 spots because we've got 4 days in our data set. and then we map the command. You can even call like a regular matplotlib command. It doesn't have to be a Seaborn. You just call something on this, all right? And so we do that, and it produces you know, histograms based on the subset of data created by the facet grid. Okay, and then if you really want to get fancy, you can create a facet grid based on multiple variables, all right? And then so here I'm calling, so we've got rows based on time, whether it was lunch or dinner, and columns based on sex. And so this would be the histogram for males having lunch, females having lunch, males having dinner, and females having dinner. Okay, so it creates subgroups of the entire data set in these facet grids. Okay, and then you have to create the facet grid, and then you map a graphing thing to each facet grid. Okay. All right, we got count plots. How much time do I have? Okay, well, I guess we'll do this. All right, bar charts. For whatever reason, Seaborn calls them count plots, and they just look like that. Okay, it's not anything impressive, but they're handy. And yeah, for whatever reason, the bar charts are called count plots, which is always like, sometimes you're like, Seaborn, I want to make a bar chart, and then you're like, what? So you have bar plots, but it creates something it's a little bit different. Okay, so the count plots are what we generally think of. Okay, and then you can also do basic stuff like LM plot. If you give it two numeric variables, we'll create a scatter plot, and then it'll also fit a trend line. Okay, and this is using a linear model along with kind of its error bars, but these are you can't get the slope and intercept. Okay, it's just like, here's the overall linear model relationship trend line, and it's just there for visual purposes, not for you to be able to say what was the slope and intercept of that thing. Okay, you can call LOS. Okay, LOS is local regression, locally weighted scatter plot smoother, and that just kind of creates a smoothed out line. And then I don't know, all sorts of stuff. If you wanted to do just create a plot of the residuals. Again, we still have no idea what the slope and intercept is, but you can just look at this and go, oh, maybe we have a problem with heteroscedasticity. Okay, you can further map some kind of categorical variable like smoker, whether someone was a smoker or not, to the regression plot, and it will color the dots accordingly. Okay, and it will also fit two trend lines, and you can see for the non-smokers, I don't know, the slope is steeper, and for the smokers, the slope is more shallow. What does that mean? I'm not quite sure, but that's the trend that we appear. Okay, and then I don't know. Here I did a facet grid with scatter to kind of just split them out as well. Okay, so this is these are just some visualization tools. I think my encouragement, again, just like everything else, is to kind of play around with it. You can do quite a bit with just matplotlib. All right, I don't want to. I know we just did some stuff in Seaborn, but you can do quite a bit with just matplotlib. But then if you're trying to do some common graphics and things like that, Seaborn is kind of like shortcuts that run on top of matplotlib to kind of create these. Like when you want to create the distribution plot with the histogram and the kernel density estimate plotted on top of that, Seaborn makes that really easy, whereas matplotlib makes a perfectly good histogram. All right, we'll stop here for now, and then I guess we'll see you guys on Friday then.